Hi everyone. In this video, get ready to talk about section 3.1 from your textbook, where we are discussing measures of central tendency. So more specifically, we're going to talk about something called sum notation, which means we're going to talk about what it means when you see the capital Greek letter sigma in mathematic notation. And we're going to talk about what I mean when I say expected value. And we're going to talk about these three: mean, median, and mode, which you probably learned about in grade school, but this is what we are referring to when we say the measures of central tendency. So remember that mean, median, and mode. We're talking about the central tendency of a distribution of a random process. So like I said, this right here, let me draw it out where there's no circles or anything going on. This is the capital Greek letter sigma, and you might also recognize a lowercase sigma. Looks like this in Greek. And we use both of these symbols in statistics very frequently, so it's important to know. Whenever we use the capital Greek letter sigma right here, we're talking about a sum. Oops. It has too many loops. Okay, we're talking about a sum of a bunch of different terms here. And so I've color-coded everything with these circles. But if I write below the Greek letter, if I write below it I is equal to 1, that means I'm defining, first of all, what I'm calling my index variable. I'm going to name my index variable I in this case. Other options that you might name your index variable might be like, for example, j. And you don't have to start at 1 for your starting point or your lower bound. You could start at 0. In many cases, we'll start at 0. Or you could even start at like 10, or for example, negative 10, right? So you can start at anything. Usually we stick to the integers, and usually 0 and 1 are good starting points. But in any case, you basically choose your index variable, you name it by placing it below the Greek letter sigma, and then you set it equal to something, and whatever it's equal to, that's what we call our starting point, or our lower bound of our summation. Whatever I write immediately in front of the sigma, or immediately to the right of the sigma, this is what we call the sum end. And the sum end is showing you what each term is supposed to look like. And then up here, above the Greek letter sigma, we write what the stopping point is. And so what you're saying is add up a whole bunch of terms where I'm allowing my index variable to vary from 0 to 100. And again, usually we're talking about the integers, and so usually we increase our index variable by 1 for each successive term. So maybe this doesn't make a whole lot of sense yet. But let's illustrate this with just some examples. So here, I is my index variable that I was telling you about. So I'm telling you my index is named I. This 1 is saying this is my lower bound of my summation. This 4 is telling me that this is the upper bound of my index variable for my summation. And this is the sum end, which is telling you that all of the terms in this summation are going to look like just my index variable. So as I allow I to increase from 1 to 4, going through all of the integers between 1 and 4, my terms are going to look like this. I'm going to have 4 terms. My terms will be 1 plus 2 plus 3 plus 4. And so of course, that capital Greek letter sigma means that we're talking about the sum, or the summation, of a bunch of terms. So hopefully this is a good way to illustrate what this capital Greek letter sigma is doing. And this, again, our previous example, as that first one. And maybe if you haven't gotten the idea yet, this is another example to contrast it with. What if I keep my same index variable I, and I keep the same lower bound and upper bound, which are 1 and positive 4, but what if I change the sum end to I squared? Well, so each term should look like I squared as I allow I to take on all of the values between my lower bound and my upper bound. And so that's going to end up looking like this summation here, which is 1 squared plus 2 squared plus 3 squared plus 4 squared. Because in each of these terms should look like I squared as I allow the values of I to go up from 1 to 4. So that's what I mean by that. So the value of the second sum would be 30. And so here's our first two examples, and then a third example on this slide is, what if I keep the same sum end, but I change my lower bound from 1 to -2, and then I also change my upper bound from 4 to +2. So now the value of I starts at -2 and ends at +2, and you can see how this sum changes to include 5 terms, because there's 5 numbers for my index variable, and how this is again equal to 10. All right, so that is the capital Greek letter and how it applies to sums. So we might see some more of those sums later on in the course. Let's talk about what we mean when we say expected value. And this is the quintessential example. Imagine you at the gas station and you're considering purchasing a lottery ticket. Now each lottery ticket you can buy is going to cost you $2 per lottery ticket. And let's suppose that you knew they were going to sell 10,000 tickets prior to selecting one to be a winner, prior to selecting a winner. And the one winner, in this case, is going to receive a $15,000 cash prize. So here's the relevant information. What is the expected value of such a lottery ticket? Well, the expected value, like it sounds, it's kind of what a reasonable person should expect that lottery ticket is worth. What would a reasonable person expect this lottery ticket to be worth? Maybe think about that for a moment. And the expected value, it turns out, is going to be the average outcome that you would expect if, and this is important, if you repeated the experiment a whole bunch of times. So imagine repeatedly buying a lottery ticket over and over and over again until you get a huge number of lottery tickets. What would be the average outcome if you played the lottery every single time, for the next 1 million years? So in this example, suppose we buy all 10,000 tickets. So this is representing playing the lottery a whole bunch of times. Suppose we buy all 10,000 tickets. Now for 9,999 of the tickets, the outcome will be $0. So those tickets, these 9,999 tickets, are worth $0, but one of the tickets is worth 15,000. And so if you wanted to calculate this average, what you would do is you would add up the value of each individual ticket. So that would be like 0 plus 0 plus 0 plus 0 plus 0. And you would add up 9,999 zeros. And then, once you added up all of those zeros, you would add up the ticket that is actually worth 15,000. Now adding zeros together doesn't really get you anywhere. So the numerator here is 15,000. The denominator, if I'm taking an average, the denominator will be 10,000 tickets. And so we get our average outcome if you were the person that purchased all of the tickets. The average outcome being $1.50. This is the expected value of the lottery ticket, is $1.50. If the expected value of a ticket is $1.50, and remember that's lower than the cost of the ticket, which was $2, this is a good argument against gambling or against playing the lottery. And actually, anytime you gamble at a casino and anytime you play the lottery, this is always going to be true because the person running the lottery, or the entity, maybe the state that's actually organizing the lottery, they want to take a cut of money. They don't want to lose money. And they're not just doing it, out of the kindness of their hearts. They're actually trying to raise money for something. So in Texas, for example, I think the state takes about half of the revenue from the lottery tickets and puts it towards education. And obviously at a casino, the casino itself has owners of the business, and the owners want to make money. And so for every game of chance, this is going to be stacked against you. In other words, for every game of chance, the expected value is always going to be less than the cost of buying in, right? So I don't remember the exact specifics of roulette, but I think there's like 40 spaces on a roulette board. And if you bet on one of the spaces and you win, I think your winnings... No, excuse me. let me restart. I think on a roulette table, and maybe don't quote me on this, but I think there's like 41 spaces. But if you win by betting on one of those spaces, your winnings are only 40 times your bet, right? So you can do the expected value calculation here. But if you wanted to break even with expected value against your bet, you would need to win 41 times your bet instead of just 40 times. And so the one space that's more is what's giving the casino an edge on expected value above your bet. So anyways, anytime you play a game of chance, this is always going to be the case, where you have the expected value lower than what the buy-in costs. Okay, let's talk about the median. So, the heights of 9 randomly selected Midland College students are given here. And so this is in centimeters, which is why those numbers look so large. But this is actually a fairly typical distribution of heights in centimeters. And this is what you would do if you wanted to find the median. And this is what we mean by median. You're going to put them in order. And so notice these are in order from least to greatest. And if they weren't, you would have to start off by ordering from least to greatest. And so that's important. Important to have your data sorted. And then after you do, here's what happens. We're going to cross off the lowest one and the highest one. And then again, cross off the next least number and the next greatest number. And we're going to continue like this until we arrive at the number in the middle. Okay? So median means middle, and mean means average. So make sure you can keep these straight in your head. If you're asked for the sample mean, you just need to average the numbers. And if you're asked for the median, it means find the middle number after you sort them from least to greatest. By the way, I don't know why my slides don't include this, but suppose you had an even number of numbers. So I'm going to have to just edit this slide really quick to represent what would it look like if instead of I had a nice odd number of numbers, what if I had an even number of numbers like this? What if I just have this as my data set for these 6 numbers? So then I go about trying to find my median. I knock off the least one and the greatest one and the next least and the next greatest. And if I knocked off the next least and the next greatest, well, I would be out of numbers. So instead, when I get down to just 2, to find the median now, what I'm going to do is actually find the average of the middle 2 numbers. And so now my median is 177. Okay. So that's a special case where this applies if you have an even number of measurements in your data set. Okay. So with that addressed, I'll give you a little bit of extra information that you may be curious about regarding the median, because I found this kind of fascinating when I learned about it the first time. The median is actually the solution to an optimization problem in mathematics, and I find optimization is one of those really, really interesting parts of mathematics that I'm always motivated to learn more about. But what number is closest to all of the data points along a number line? This is the optimization this is the optimization problem I'm talking about. Is that if you're given a data set, and we say that each measurement in the data set is a data point. So maybe I should have used the word measurement. From a data set. The problem is what one number is closest to all of the measurements from a data set along a number line. And so we're gonna call this absolute value of a minus b. This is going to be the distance between points A and B along a number line. And this should be pretty intuitive. If I draw a number line up here, and so here's like 0, here's 1, here's negative 1, and let's say that this point is point B, and this point is point A. This distance between B and A, this would be the difference between B and A. And in case you took these points in a different order, we use the absolute value sign so that that distance is always a positive number. You can't ever have negative distance, right? So that's how we come up with this formula for the distance between points A and B along a number line. And if we are given 9 data points, we're asking the question, what new point on the number line, so not one of those 9 data points, but a different point, what new point on the number line will minimize the distance between this new point and the existing 9 data points? In other words, going off the same problem and just sort of rewording it, what value of x tilde gives the minimum value of the function f of x tilde, so my function's name is f, where I define my function as this. This is saying it's the sum, right? The capital Greek letter means sum. We're talking about the sum of the distances between a data point, or maybe I should say a measurement, one of the measurements that belongs to my data set, and the new point that I'm talking about, x tilde. So here's the new point that we're talking about adding in, and then this, and I just say a measurement, I'm talking about that. And I use the little subscript I to show that I have a bunch of different measurements, right? So this is my data set that I've shown you in the bottom here, and I might number off these data points as like x1, x2, x3, x4, x5, and so if I ask you what is x7, the subscript, that'd be 183, right? 6, 7, and so on. And what this summation is telling you is that I'm going to let my index variable range between 1 and n, where in our case n is just the number of measurements. And so we have 5, 6, 7, 8, 9. So we say n is equal to 9. So we're going to let the value of I, my index variable, go up from 1 to 9, counting all of the integers in between. So it's actually going to cover x subscript 1, x subscript 2, x subscript 6, x subscript 7, x subscript 8, and x subscript 9. So all of these measurements are going to be included in the sum. We're going to sum up the difference or the distance between each of these measurements and some new value, which we're calling x tilde, for the whole data set. So if our new value x tilde is something very far away from this data set, so you notice my data set goes from about 168 to 197, and if I pick some number for x tilde being like 0, that would be pretty far away. That would make my f of x tilde that would be large, right? Because the difference or the distance between 0 and all of these numbers is a really large number. If I let x tilde be really large in the other direction, like 1 million, that would also make my function value very large. But if I pick some value of x tilde equal to something that's like maybe in the middle here, like 174, for example, that's kind of in the middle of this data set, that would actually give me a value of f of x tilde that was relatively small. So depending on my choice of x tilde, that gives me a different value for this function, f of x tilde. And what I'm looking for in the end here, to solve this optimization problem, is I actually want the minimum value. So I want the smallest possible value that I can get from my function. And again, maybe I've already spoiled the fun here, I've already given you a spoiler, is that the median is the solution to this. So if you're wondering, how do I minimize the value of this function? How do I minimize the distance between x tilde and these other points in my data set? Well, you do that by choosing x tilde equal to the median. So this is what it would look like if I plot this function, which is the sum of all the distances. If I plot this in blue, it would be this curve. And so if I let x tilde take on all of these different values, like if I let x tilde be 195, it would return a certain value for my function, which would be like 150 or so, right? That's how you read this chart. And you can see the very minimum value that I could choose for x tilde happens here. And so this is actually the true value of the median, is where this function finds its minimum value. By the way, in orange, these are just my data points. And so like this is x subscript 1, 168, and that corresponds to that point. And this would be x subscript 9, 197, and of course 197 can be found right there. Okay, so this is just showing, again, both the median of this data set and the minimum value are actually the same. Okay. Let's talk about now the mean. Remember, mean means average. And like we talked about earlier with expected value, the mean is also the expected value. And that's going to be important because obviously there's some real world scenarios, like in gambling or playing the lottery, or really talking about any random process that you're going to repeat many, many, many times over, where this is something we care about. We actually care about what is the expected value. So let's talk about the mean. The heights of 9 randomly selected Midland College students are this in centimeters, and so this is our data set again that we've been dealing with. If I wanted to calculate the mean, we just have to sum up all of these values. So I call my data set x, which means this is x1, and this is x2, and so on. This would be x9. And so I'm going to sum up all of these values x with subscript I, so that means I is my index variable, and it's going to go from 1 to n, where n is my number of measurements, and that would be 9 in this case. And then I'm going to take that number and divide it by n. And this is how I get my sample mean. And we use x with a bar above it to talk about the mean, or the sample mean, and we use x with tilde to talk about the sample median. But anyways, what that looks like whenever I add up all those values is this. The sum of all those values, that summation, is going to be 1605. And then the denominator here is 9 because I'm dividing by n. And so then I get our answer, which is the mean of 178.3. Okay, so a little bit of trivia that, again, I found really fascinating when I was learning about the mean. And I want you to remember this, what we're talking about here with this optimization problem and how the mean is the solution to this particular optimization problem. Because we're in chapter 3 right now in your textbook, talking about descriptive statistics. But next week we'll be in chapter 4 of your textbook, talking about how to make a really simple math model called a linear regression model. And in that case, we're going to sort of extend this idea that we're learning about right now. So don't forget this before next week. I will definitely be referencing this discussion next week in class. So the mean is the solution to a different optimization problem. So the optimization problems in math, if we didn't pick up on this already, they could either be finding the minimum of something, like with the median, we were trying to find the minimum distance from the median to all of the data points or all of the measurements in our data set. Or optimization problems in math could also be talking about finding a maximum of some function. And in our case, the mean and the median both find the minimum value of some function related to the measurements in our data set. So we define a minus b absolute value as the distance between points a and b along a number line. And we've already spoken about why that is, and I drew a number line for you on a previous slide. But what I want to emphasize now is that if I just square that, that allows this quantity to be the distance squared. And then if I just take away the absolute value, you'll notice that it doesn't really change anything, because if you take a negative number and then square it, that would be like negative 5 times negative 5, which you know is positive 25. So squaring a negative number always gives you a positive. So we have 9 data points, and we're asking the question, what new point on the number line will minimize the distance squared between this new point and the 9 existing data points? I'm going to call our new point that we're talking about x bar. And again, we're looking for the minimum value of a function, which I'll name g of x, where I define the g of x function as this. We're talking about the sum of all of the distance squared between measurements and this new point. And whenever I select the right new point, the right x bar, that will be our mean. So how do I select the correct new point? Well, let me show you what it looks like. If I represent this g of x function in blue as the curve, or sorry, I should say g of x bar, and so in my horizontal axis, these are different possible values I could choose for x bar. If I choose, for example, 190 to be my value for x bar, the way you evaluate this function is you would say the corresponding value of this function, g of x bar, would be about 2,000. But I want the minimum value of this blue curve, and the minimum value of this blue curve seems to appear right here. And so the value of x bar that corresponds to this minimum value, that's going to be actually the mean. So the value of x bar that corresponds to the minimum value, this is actually the mean. And that's kind of neat to know that this mean is really the solution to a particular minimization problem, or we could call a minimization problem my optimization problem. So we're choosing an optimum value in a way, because we're choosing the value that is, minimizes the sum of the squared distances. And again, these orange dots represent data points or measurements from my data set. One last thing before I move on This SST stands for the sum of squares total. That's where SST comes from, is from sum of squares total. And this is just another word for this function. So it's a sum, obviously, because I've used the little summation, and squares just means the squared distances. And total means, well, it's kind of redundant. It's kind of like, I can't think of any other word to describe it. By the way, when we're talking about the mean, whenever you take some, measurement, like this is x to the fourth, x with subscript 4. If you take the difference between some measurement and the mean, which we use x bar for the mean, this is what we would call a deviation. So if you see the word deviation anywhere in statistics for the rest of the semester, we're talking about the difference between just one measurement from my data set, the distance between that measurement and the mean. And again, here on the slide, I've just illustrated that the mean that we found earlier, the average between all these data points, it was 178.3, and that precisely corresponds with the minimum of my G function, or my SST function. Just to compare and contrast median and mean. Median means middle, mean means average. Median is kind of a nice measure of central tendency because the median automatically filters out outliers. So notice the way we calculated the median is we just crossed off the least data point and then crossed off the greatest data point and then continued like that. So if you have any outlier, and by the way, maybe I never mentioned this, but by the way, an outlier is just an extreme value. You might say an extremely low or extremely high measurement. If you had an outlier, the median automatically filters out that outlier because that will be, one of the first measurements that we're going to cross off as we're looking for the middle value in our data set. And so that's kind of cool. On the other hand, the mean has something going for it as far as a useful measure of central tendency. The mean is actually the expected value. So if we're asking the question about the lottery, and what the value of one lottery ticket is, if you found the median value of the lottery ticket, of course it would be 0, because the winning ticket, 15,000, that would be the first value you cross off, right? Because you'd cross off the least and the greatest measurement from our data set first. And so we'd get rid of the winning ticket and then we lose that valuable information. So if you actually want the expected value, then the mean is important. The median is a useful measure of central tendency because the median solves an optimization problem. It minimizes the sum of the of the absolute value of the distances to data points. A median is also useful for gauging the typical outcome. So we use the median for examples like asking what's the median salary of, dentists, for example. If you're considering becoming a dentist, chances are that you're going to be, at some point in your career, about the median dentist in terms of salary. And so if you're evaluating whether you want to become a dentist, you might Google search something like median salary. And that would be more important than finding the average salary, because the average salary is going to include maybe some dentists that make just a ridiculous amount of money, right? Maybe celebrity dentists or the president's dentists or something like this that make way more money. They might actually skew what the mean salary of dentists are, but the median is sort of what we consider typical for salaries of dentists. We also talk about median household income. If you're wondering, what's the quality of life in a particular city, you might ask what's the median household income of that city, because that would be like a typical household. Going back to this side where we're talking about the mean, not the median. The mean is good because it minimizes the sum of squared deviations, or the SST. And so Again, we talked about how that is a particular optimization problem and how it's cool that the mean optimizes this. And again, the mean is useful as a measure of central tendency for gauging the overall effect of many trials of an experiment. And so if you are going to be buying replacement parts for a machine over a really long lifespan of a machine, you actually care about the expected value of the lifespan of a particular part and not the median value or the typical value, because after you use many parts of that type, what's going to matter for you in running your business is actually the expected value, because you're going to be using so many of those parts. And again, in baseball, we talk about batting averages and not batting medians, because maybe what you care about is how many hits he gets after many hits. Baseball players have a lot of opportunities in their career to be up to bat, and so we care about a batting average. So they're actually, median and mean are both useful, they're just useful in different circumstances. And they're both cool in that they solve an optimization problem, they just solve a different optimization problem. And they have different values as measures of central tendency, the median because it automatically filters out outliers, and the mean because it's the expected value. So it has an additional sense of importance for us. Okay, vocabulary. The population is the set of all individuals or all possible outcomes. We've actually learned this before, I think. The sample is going to be a subset of the population that you've measured. Again, I think we've gone over this in chapter 1. The deviation is the difference between a measured value and the mean. So again, measured value and the mean. And obviously taking their difference. SST is the sum of squares total, or the sum of squared deviations. And so there's a formula for SST, and so remember that acronym. We're going to come back to that again in chapter 4. The sample median is the middle of your data set. And the sample mean is the average of your data set, or the expected value. An outlier is a measurement with an excessively large, that's not good, I need to fix that word, an excessively large deviation relative to the others. Data is information about the measurements on your sample, so used interchangeably with sample whenever you actually have the data, or you could just say it's the measurements on your sample that you take. Descriptive statistics are just numbers that summarize data or describe a sample. So what we've been talking about is descriptive statistics, right? If we talk about the mean or the median or the mode, these are all descriptive statistics. And there's other descriptive statistics that we'll talk about in the next video. Inferential statistics, we are not talking about these yet, but we will later in the semester. And these are numbers that summarize what we know about a population. And you use inferential statistics when you make decisions. That's when they become important, right? So if you're about to make a decision, you don't just want the descriptive statistics, but we're actually going to talk about how inferential statistics can really guide good decision making. Again, later in the course. And a parameter is a number innate to a process or a characteristic of a random process. And in most cases, we'll never know a parameter's value, but we can estimate it. And remember that a statistic is just an estimate of a parameter. So here's some examples of descriptive statistics and the parameters that they are estimating. So the sample mean is an estimate of the population mean. And the way that you read all of these actually is you would say this thing over here is an estimate of the thing on the right. So the sample mean is a descriptive statistic, which is an estimate of the population mean. We use Greek letter mu to refer to the population mean. The sample variance, we use lowercase s squared to talk about sample variance. That's just an estimate of the population variance. And this is a lowercase sigma, which is also a Greek letter. And that mu, I should say, is also a lowercase Greek letter. The sample standard deviation, we use lowercase s. The sample standard deviation is an estimate of the population standard deviation. The sample median, and we use x tilde, is an estimate of the population median, and we use mu prime to talk about the population median. In Excel, we're going to generate a data set and we're going to calculate the mean, median, and mode. And I think we're also going to do this in a calculator as well. And so we're going to do this in this video in a TI-84 emulator, so you can see what that looks like. Let me just open up an Excel workbook. Okay, so here you're looking at Microsoft Excel. And to create a random data set, here's what I'm going to do. I'm going to decide on a population mean and a population standard deviation. And I'm just arbitrarily choosing these because I'm just making a simulated data set for you guys. So I'll let the mean be 50 and the standard deviation be 10. Okay. Now I'm going to let my data set exist in this first column. And I'll just create like 7 numbers, let's say. And I'm going to type equals in cell A1 equals norm.inv open parentheses rand open close comma. Now it's asking me for a mean, so I'm going to click on my population mean, and then comma, my standard deviation, and I'll click on my population standard deviation that I chose arbitrarily, and then do close parentheses and click enter. So it generated a random number for me, which is 40.6, and I can use the bottom right hand of this cell to drag it down to 7, so I get 7 random numbers, right? In theory. Let me show you what happens. So the first one worked and the second one doesn't, and we'll also look at really quick why this formula doesn't work. If I click on it, I can see that my formula is now referencing these cells that have shifted down a little bit. So let me show you how to fix that. I can go over to here where it says D3, and I'm going to put a $sign in front of the 3, so it will lock in that cell reference to row 3, and a $sign in front of the 4, so it will lock in that cell reference to row 4. Click enter. And now again, I'm going to select cell A1 and then click on the bottom right corner, hold it down, drag it down through 7 numbers. And now I have 7 random numbers that follow a normal distribution, probability distribution. And so these numbers may have come from some random process, like maybe you're measuring the height of penguins in centimeters or something like this, and you could have gotten these 7 measurements. I don't know how close. I'm sure some species of penguin has around these heights. Just to make it easier on myself, I want to round these down to the nearest, whole number, and I don't have a bunch of decimals trailing. And so to do this, I'm just going in front of this equal sign, I'm going to type in round, open parentheses, jump to the end and do comma 0, close parentheses, and that just rounds it to the nearest whole number. Now that I have a random data set, I don't want it to change, so I'm going to select it, copy, go to the paste drop down, and just do paste values so that I don't have to worry about these numbers changing on me, because one thing that happens with Excel is anytime you hit the enter button, it will just generate random numbers for you again, and you'll lose your data set. So here we go. Notice if I want to take my sample mean, which we've learned about this video in Excel, I could type equals and then add up all of these numbers just using the plus sign, and then that would actually be the sum of all the data. And then if I want to take the sample mean, I'm just going to take that sum and divide by the number that I have, and I have 7 right here, so I have 144 as my sample mean. That's pretty close to my population mean. And this is just an example that, like, in real life, you don't get to decide what the population and mean and standard deviation are. all we can do in real life is take measurements and calculate a sample mean, and the sample mean will never ever be the population mean itself, just like 44 is not the same as 50, but our sample mean is an estimate of the population mean, so we expect 44 to be close to 50. We expect the sample mean to be close to the population mean. In real life, we'll actually never know these numbers up here. Okay, what was I going to do next? Oh, so we calculated the mean. Another way to calculate the mean, rather than taking the sum and dividing by the number, is you could do this. We'll restart, and right here in the cell, we'll type in equals sum for sum, and then I can select this range, close parentheses, divided by count. So I can count the number of measurements in this range. So if I didn't know how many measurements I had that could come in handy, it would tell me that I have a sample mean of 44, which is like what we got before, so that's just another way in Excel. If you know those cell formulas, that could come in handy. And if you're familiar with Excel, you're probably saying to yourself, man, we're wasting our time. What are we really doing here? So if I wanted to find the sample mean, I can also just type equals average, and then average over the column A by typing A colon A, and bam, 44. So the average formula in Excel will give you the sample mean. I also promised a way of calculating the median and the mode, so let's talk about the median and the mode. If I want the sample median, what I can do is sort this group of measurements from least to greatest. So I'll select column A in Excel, and then I'm going to go over here on the ribbon to sort and filter, and then there's an option that says sort smallest to largest, and that's exactly what I want. And what the median does is that it says I should mark out, just get rid of the least measurement, and then the greatest measurement, and then the least measurement again, and the greatest again, and the least again, and the greatest again, until what I'm left with is the median. So the median must be 46. And that's a perfectly valid way of doing things. A little shortcut here, if you are Excel savvy, is selecting the cell here where I want my sample median. Type equals the word median, open parentheses, select the first column, A colon A, close parentheses, enter. Also gives me 46 for the median. And like I said, if you have a set of data that has an even number of measurements, like if I throw in an extra number 27 here, what it does is it's going to find the middle two measurements, and it's going to take the average. So I think this is the average between 39 and 46. It's 42.5. Okay. And then lastly, I told you about we were going to calculate the mode in Excel. So if I calculate sample mode, let's see what happens. I do equals mode, A through A, and it says there's no sample mode. So theoretically, when we talk about distributions, I told you that, given some distribution, the mode of the distribution, so let me just, the mode of the distribution was the point that was the maximum probability in a probability distribution, right? So this vertical bar right here would represent where the mode is in my distribution, right? That was in a previous video lesson. And yet, whenever we talk about the sample mode, what we're talking about is the value that appears the most times in a particular data set. So the measurement that appears the most times, there's not really one in this data set because none of these values repeat themselves. But for example, if instead of 47, if I measured the number 46 twice, then my sample mode would be 46 because 46 appears twice in this data set. Likewise, if I measured the value 35 two times, then 35 would be my sample mode. So you don't always have a sample mode if none of your measurements repeat. And honestly, just as a little bit of editorial here, I don't think the sample mode really means anything for quantitative data, because having a measurement repeat itself does not necessarily mean that it's towards the center of the distribution. Theoretically, when we have a distribution that we come up with in theory, the mode really does mean something. It's the maximum probability. That's for a continuous distribution, but in this case, I don't know that the mode necessarily means a whole lot when you have a small amount of data measurements from a quantitative source. Maybe if you have a lot of measurements and the variable that you're measuring is discrete, sample mode might mean something for that data set. And certainly whenever you are dealing with nominal data, where you're sorting cars by color or by make, or you're sorting people by their profession, mode would mean a lot, because you wouldn't actually be able to take the mean or the median car color, but you could take the sample mode, which is what car color is the most popular out of your sample. So anyways, we won't really use sample mode very much, and we definitely won't use it for continuous data, because that won't make any sense. You shouldn't have any repetitions if you have a continuous response variable. Okay, but that's just an introduction for using these in Excel when you're working on your project later this semester and in a few weeks from now. You'll want to know how to do these calculations in Excel. So be familiar with that. And to show you how to do mean, median, and mode quickly in a TI-84 calculator, let's actually use the same data set, and let me load my calculator. So in a TI-84 calculator, if you want to find the mean, median, and mode of a data set, what we're going to do is first get your calculator out and go to Stat, the button that says Stat. And then the first option here on the list is Edit, so we click Enter to choose Edit. And then you'll see several columns, and at the top it says L1, L2, L3. These are different lists, and what we're going to do is put this data that I randomly generated into a list. So I'll punch in 29, and then below that 35, and below that 39, and below that 46, below that 47, below that 50, below that 62. Then, when we are done, we're going to go back to Stat. And by the way, when you're done, just double check really close and make sure that you put all of your numbers from your data set into list number 1 in your calculator. Otherwise, your descriptive statistics that you'll get from your calculator will be way off. So we go to Stat. We're going to go right, so we're going from Edit to Calc. And then we choose one variable statistics, which is the first thing on the list. We click Enter, and down arrow, we want to obviously calculate list 1's one variable statistics. So clicking Calculate. I want to describe this really quick. So where it says X bar equals 44, that's talking about your sample mean. When it says the sum of X, that's talking about the sum of the entire sample, so that should be 308, and it is. The sum of X squared is 14,256. So if I squared all of these values and then sum them up, I would get that. That doesn't really mean a whole lot to us, so you can mostly just ignore that. Where it says S, the letter S with subscript X, equals to 10.83, that's something called the sample standard deviation. And the sample standard deviation is found in Excel with equals stdev.s, open parentheses, and then you select the group of measurements, and that's 10.83 in Excel, and it's 10.83 in your calculator. Below that, where it says sigma x, ignore this. Please don't ever use the sigma x that your calculator gives you. I'll talk about that in a later video. Here it says n equals 7, so that's saying that you have 7 measurements in your data set. And then what follows tells you the minimum value, 29, the maximum value, 62, the median, which is 46, and it also tells you the first and third quartiles of your data. So Q1 is your first quartile, Q3 is your third quartile. Your median would be your second quartile, but it's also the median. And we'll talk about those 5 numbers in a later video. But we found the median and we found the mean from our one variable statistics. And actually your calculator doesn't tell you what the mode of your set is. You have to recognize that yourself. So we did this in Excel and in your TI-84. Let's talk about a vocab word called resiliency. So we say that a measure of central tendency is resilient if outliers don't affect it very much. So in order of most resilient, outliers do not affect the mode very much. So this is most resilient to least resilient. The median is more affected by outliers, and the mean is the very most affected by having outliers present in the data. So that's if you were asked about resiliency of a measure of central tendency. I typically don't ask about that on exams, but it may come up in homework. And then let's talk about skewness. So if a distribution is symmetric, then the measures of central tendency should be approximately the same. If a distribution is skewed left, meaning the left tail is fatter than the right tail, then this is how they're going to appear from left to right. For a skewed left distribution, we're going to see the mean appear first, and then the median appear second, and then the mode appear third. If a distribution is skewed to the right, which means the right tail is fatter, versus the left tail being fat for left skewed distribution, then this is how they're going to appear. Mode will appear first, median will appear second, and mean will appear third, as you would read it from left to right. This is important, so I would say that you must memorize this slide. And let me show you what I mean using Desmos.com. So here's a page on Desmos.com, and what I want to draw your attention to is this red curve. So this red curve represents a probability distribution. And I can make that red curve symmetric, like so. It would be a symmetric distribution. And I can change the shape of that distribution and still have the distribution be symmetric. Symmetric just means that the left tail and the right tail are equal, meaning that the area under the left portion to the left of the mode and the right portion to the right of the mode are equal. Remember, the mode is the maximum point in this probability distribution. If, however, I choose to make this distribution skewed like this, let's see, I'm going to allow just the mode to appear. So the black line is the mode, the maximum point. This would be left skewed because the area on the left side of the mode is much larger than the area under the curve on the right side. So this is the left skewed distribution. If I add the mean and the median, I want to show you that for a left skewed distribution, what appears is mean, median, mode from left to right. So in orange, we have the mean. In purple, we have the median value. And in black, we have the mode. So this is mean, median, and mode of a left skewed distribution. That's how they appear. That's why I wrote mean, median, mode under skewed left for this slide. Okay, so same measures of central tendency, same distribution. I'm just going to make it right skewed instead of left skewed, so adjusting my parameters. And I get a right skewed distribution. But notice now it's mode, median, mean. So when it's right skewed, the way that these measures of central tendency appear from left to right are mode, median, mean. Whether it's left skewed or right skewed, the median is in the middle of those distribution, or of the measures of central tendency. So that's easy to remember. Median meant the middle The sample median is the middle measurement of your data set anyways, and now you know that whether your distribution is left skewed or right skewed, the median should always appear in the middle of your 3 measures of central tendency. The mean, you can remember its location on a distribution because the mean is the least resilient towards outliers. So if you have outliers, the mean is always closest to the outliers. And so in this red distribution, I would say my outliers are on the tail over here on the right side, and of course the mean, being in orange, is closest to the outliers. So that can kind of help me remember the order here. Lastly, we talked about level of measurement in chapter 1. And so I want to bring that back and just talk about which measures of central tendency actually apply to different variables with different levels of measurement. Well, if you have a nominal level of measurement, which is just placing individuals in your sample into categories, the only measure of central tendency you could take is the mode, which is to say which category contains the most individuals. If you have an ordinal level of measurement, and to remind you, because ordinal can be tricky, ordinal, our example was like the survey at the grocery store, where they were asking customers, are you, very satisfied? Are you somewhat satisfied? Are you not satisfied? Or are you very unsatisfied? Right? That was sorting individuals from the sample into categories based on how they felt about the grocery store. But you actually could take a median. You could find, the customers ranked between groups A, B, C, and D, and you could take the median. So let's say there was a total of 50 customers that participated in the survey, hypothetically. And let's say that out of those 50, 2 were very unsatisfied, 8 were not very satisfied, 15 were satisfied, and 25 were very satisfied with their experience at the grocery store. Well, let me tweak these numbers a little bit. Choose better numbers for my example. Where would the median person be? Well, actually the median person would belong to group B, and so we could actually take a median of an ordinal data set, because again, ranking these individuals, well, there's 20 and very satisfied, 20 and satisfied, 8 and not satisfied, and 2 and very unsatisfied. So the median out of 50 individuals, or maybe we should say 51 individuals, the median person would be the 25th respondent, or maybe it would be the 26th respondent. And the 26th respondent, ranked from satisfied to least satisfied, would actually fall into this category, right? Okay. Interval and ratio, you can take mean, median, and mode, because, why not? My example for interval was temperature in degrees Fahrenheit, and so obviously if you have several days in a row, you can take the mean of those days, you can take the median or the mode temperature in Fahrenheit, and ratio, my example in a previous lesson was like kilograms of some product. Well, for any weight that you're measuring, you can have the mode, median, or mean of the measurement. Where again, I don't really like the idea of mode for interval or ratio measurements because these are quantitative, but technically it means something. All right, I know this is such a long video. Thank you for making it to the end. There's just a lot to say about Chapter 3.